Channel, we still continue in discussion of our paper on anomaly detection, which is the Skip-GANomaly. And in this session, we'll be looking at the third component of the loss function, which is the latent loss. Now, the latent loss it's not explicitly visible from the architectural diagram, but it is shown in this equation 3. And the author claims that the essence of the latent loss is the representation, uh, the latent representation of the f of x and f of x bar, which to be taken by z and z bar respectively, to be as close as possible. So that is this to ensure that data is capable of producing contextually sound latent representation for common examples. And what they are using here is the L2 lum. So now the X is taking sample from the probability distribution of the normal instances, and this F represents the discriminator. That's the function, that's the neural network. So it seems to me, but when we get to the coding part of it, the implementation, we get more clarity. It seems to me that it's resembling what you have in a semis network, because they said they use the final convolution layer of the discriminator and they extracted the features of x and x bar. And as we see here, that we have x and x bar is fed into this discriminator. To me, it seems as if they are sharing the discriminator as a shared backbone. So at the final convolution, they now have like two, where we have this 100, maybe that's their z in this situation. So they are now having a latent vector that like go this way and the other one goes this way. That's my intuition. So they have a two head, so 100 here, 100 here, and they now learn this loss function to be able to optimize that. It seems start of like a CMS network, if you get what I mean. Alright, so that's just that about the latent loss. Now, in wrapping up this session, let's look at the overall architectural, the proposed approach, which is the same thing, very close to figure 3. So here we have the X, which is sampled from only the normal images, and we have the X bar, which is the reconstruction and is optimized to be as close as possible to X. Of course, we have the latent vector. This is the latent space vector. So, and they use the skip connection. So that's what this black arrow means. That is the skip connection. In their own case, they actually concatenate the features from each of these. From here and here, they concatenated the features from this encoder to the decoder. And also, they fed the reconstruction from the decoder output and the original normal samples. They fed them into the discriminator. So the discriminator is a function that is taking the two samples. And now they now optimize three loss functions. The first loss function is what they refer to as the contextual, often called the reconstruction loss. So they call it the contextual loss, and that's to make sure that the x bar is as close as possible to x. Then the next one is the adversary loss, which is the standard GAN loss, just to make sure that the discriminator get to a point that is unable to distinguish between the normal samples and the generated samples. So such to force the network to generate samples that is as close as possible to the original normal samples. All this learning process forces the network to be able to model the distribution of the normal samples, such that during inference it will be able to have a very high reconstruction error for the abnormal instances. Now, the third part of the loss is what they refer to as the latent loss, and essentially what's happening here is they are splitting out this head because two inputs are coming here, so they're splitting out the head into two latent vector, and the first one is z, which is the one coming from the x, and the second one is z prime, which is the one coming from the x bar, and they want this to learn this objective to make sure it's as close as possible, so they want to minimize this objective. All right, thank you very much, and see you in the next one.